we will get started. So today's lecture is what I call case studies. We're going to explore heat capacity. It's not strictly speaking new material, but it definitely is worth going into in a little more depth and a little more slowly than we've seen it so far. Today's lecture is all about heat capacity. And for those who are just joining, the lecture notes will be out shortly. So this is heat capacity, and I hope to convince you that these are keys to the kingdom, or at least the thermal kingdom. Right, heat capacity is not just another coefficient. It's the thing that you're going to need to know to solve many problems in material science. So let's see, Gibbs free energy, right? Equilibrium at fixed T and P is balanced between H and S. So this you already saw. This you saw on day one with the baby book and then with the hot and cold packs. Right, we're balancing enthalpy and entropy to find equilibrium. All right, so if you're going to balance two things, if they're really important, how do we calculate them? How to calculate H and S for a given phase at a given temperature and pressure. Right, doing this sort of calculation is going to be a lot of what we're doing going forward in O2O. So let's step through that. Let's start by calculating H. Calculating H of T at a fixed pressure. Start with H. All right. Back to the beginnings. H equals U plus PV. So DH equals DU plus P dV plus V dP. This is the chain rule. All right, that's the chain rule. Then we're going to use the combined statement. This is T ds minus P dV plus P dV plus V dP. This is using combined statement. And canceling terms, we have T ds plus V dP. You did something like this on the P set, so this should be familiar. So combining this, TH at fixed P equals T ds equals dQ reversible, right? That's why the enthalpy was often called the heat. And of course, we know this equals Cp dt. So the change in enthalpy is calculated by the heat capacity. All right. So what that means, we're going to use the fundamental theorem of calculus to express enthalpy at some T2 as a function of fixed pressure is going to be the enthalpy at some T1, the same pressure, plus the integral from T1 to T2, the total differential dH, and plugging in from above, this equals H T1 at P plus T1 to T2 dt Cp of T. So in order to calculate the enthalpy at some other temperature based on reference data, the enthalpy at, let's say, a reference temperature, we need this heat capacity data, which in general is temperature dependent. So there's data we need. What about entropy? calculating S at T for fixed pressure. All right. ds equals Cp over T dt minus V alpha dP. There's many ways you can get this. You could just go to table 4.5, or you could derive it. So that means that ds at fixed pressure equals Cp over T dt. So again, using the fundamental.
Sorry, would it be possible for you to write with like a bigger tipped marker? I'm kind of having trouble reading the details.
Sure, let me try to do that. It's always
okay with everyone.
Yeah. No, I appreciate those sort of comments, because it's, I know that Zoom also samples things differently, and I see it differently on my screen than you see it, which is also different than you see it in the recording because of the way Zoom samples for bandwidth issues. So, all right. So we're going to use fundamental theorem of calculus again. S at T2 at a given pressure equals S at a T1 at that pressure plus T1 to T2 ds, and we can put equals S at T1 pressure plus T1 to T2 dt, and the integrand is Cp at T over T. So again, we need Cp as a function of temperature to do that calculation. So again, we see for both enthalpy and entropy, the key to calculating these things for varying temperature is knowing the heat capacity function or the heat capacity data. So we're going to use these expressions so much in this class. Let's talk a little bit about where heat capacity comes from. What is Cp of T for real materials? Right, we know for ideal gases, it has this really simple form, like 5/2 R for a monatomic ideal gas. But, you know, we're interested in real materials and material science. We don't make cars and medical implants and computer chips out of ideal gases, right? We care about the real stuff. So let's start with a relatively simple model. Consider bonds as atoms on springs. All right, we're going to consider bonds or atoms on springs. Sounds good. All right, let's draw bond energy as a function of displacement. I trust everybody has seen something like this before. If not in 3091, then in another introductory chemistry class. And let's see, so U is a function of R. This is energy as a function of atom to atom spacing. And you typically have something like this, right? That's going to be your bond energy as a function of distance. And there's an equilibrium position that's called R naught. And let's just say that my atoms are sitting there at that displacement. Let me draw my atoms here. Here's a spring, right? And they are at distance R naught from each other. Let's say that I'll call this atoms are quiescent. right? They're just sitting there. So this is a low, or I say lower energy state. It's also lower in entropy. There's no disorder. There's no sense of mixed upness. You know exactly where your atoms are. Lower than what? Lower than what? Let's draw a higher temperature state. Again, there's R, U. I can never draw the same thing twice, so let's see what happens here. It's not too terrible. All right, so now R naught is still the same. But let's say that now I have more energy in the system. So my atoms are oscillating. They're vibrating around. I'll say there's some sort of, all right, they're vibrating around that minimum. So let's draw that over here. Let's say that this is R naught. But as drawn here, the atoms are a little bit closer together. They've compressed the spring. Right? And they're on the move. They're vibrating, right? So the atoms are vibrating. So you can see from this picture that the system is in a higher energy because there's an average energy of the atoms that's increased here. And there's also a higher entropy because there's an amount of disorder associated with the location or the vibrational state of the atoms. So this is higher energy. Sorry, I said I was going to write with a fat marker. Higher energy and higher entropy. So that's a relatively straightforward concept. You can do a lot with this, right? There are models. I should say models for the heat capacity as a function of temperature that consider vibrations. Of atoms right, vibrations of atoms and crystals. That's what we just drew. We drew a simplified model of vibrations in atoms and crystals. There's a word for these. What are vibrations of atoms and crystals? Those have a fancy name.
Is it oscillations?
It could be called oscillations. That's a little bit of a fancier name. There's also a name phonons, which is a lattice vibration. So there are different models. There's the Einstein model. This is a simple model. All vibrations have the same frequency. It's simple, but it was a first important test of quantum theory. And there's a fancier model. There's the Debye model, which is that there's a range of available vibration frequencies. A range of frequencies. And this range is associated with range of wavelengths. That goes beyond our class, but I wanted to mention this. We will solve these models later. using StatMech. So later in the class, when we come around to statistical mechanics, we're going to solve for the heat capacity of solids using these models. So that's kind of neat, but we're not ready for that yet. So let's look at some slides. Let's look at some data. All right. So this is just an example of heat capacity. Sorry, there's a little bit of resolution issue here, but this is the heat capacity at constant volume, in this case, of aluminum as a function of temperature. And this is reduced temperature. It is temperature over something called the Debye temperature. And the Debye temperature is characteristic of the highest energy vibrations in the solid. This is a concept you'll encounter in later classes. So the circles here are data, and the solid lines are models. And you see that the Einstein model and the Debye model both show heat capacity going to zero at zero temperature. That's kind of interesting. And they both also show the heat capacity saturating, right? Heat capacity comes up and it saturates at high temperature. But the Debye model is a little more accurate, right? It captures that temperature dependence better than the Einstein model. So we'll come back to that. Here's another interesting comparison. These are the heat capacity for lead, silver, aluminum, and diamond. And at any given temperature, let's say 10 to the 2. So this is what, 100 Kelvin. At 100 Kelvin, the heat capacity of these four elements is very different. But there's a self-similarity in the shape of the curves. So there's some underlying physical law that describes the heat capacity of all these materials. And it's the Debye model, which we just, were introduced to. The difference here is that diamond characteristic lattice vibrations are at a much higher energy than lead's characteristic lattice vibrations. That comes down to bonding, it comes down to structure, and it comes down to the weight of the atoms. Lightweight things vibrate faster than heavier things. It's true in atoms, it's true in swings. So this is interesting, and the circles here are data, and the solid lines are models. So you see the Debye model is really excellent. Another thing I'll point out is that they all seem to converge at the same number. This is an early law. It's not really a law, it's just an empirical observation, the law of DeLong and Petit, which is that the heat capacity at high temperature converges to 3R for all solids. And it's a decent approximation for solids at high temperature. If you need to estimate the heat capacity of a solid and you have no data at your disposal and you're in a hurry, 3R is not a bad estimate. R is 8.314 joules per Kelvin per mole. So 3 times that is roughly between 24 and 25. And that's what you see. If this data were taken up high enough in diamond, you can kind of imagine that diamond would also converge to that law of DeLong and Petit. I want to talk about cobalt.
Sorry, I had a question.
Ryan,
So
please.
like these graphs were plotting CV, C sub V. Do these trends also hold for C sub P?
Yeah. So one thing which we'll start to learn with experience is that for solids at atmospheric pressures and the kind of pressures we encounter for most materials processing and most industrial processes, CV and CP are very similar. Pressure dependencies with solids don't matter very much unless you get to very, very high pressure. So everything you just saw for these solid phases pretty much applies the same whether you're at CP or CV. And we'll start evaluating those differences quantitatively later on in the class. One way to think about that is it takes a lot of work to squeeze a solid, as opposed to a gas, which we can imagine takes less work. Good point. All right, let's talk about cobalt. Why about cobalt? I think it's interesting to read a phase diagram. We haven't really done that yet. This is a unary phase diagram. Let me bring out my laser pointer. All right, so this is pressure and this is temperature. Somebody, how many different phases are pictured here?
Four.
4. Can you name them?
I see 3 different solid phases of cobalt and then liquid.
Right, liquid at a high temperature. If you kept on heating, presumably you get the gas, but this is a high pressure phase diagram. These are in gigapascals, so these are high pressures. This over here is 100,000 atmospheres. So this is high pressure stuff. And then as you cool down, you have an FCC structured paramagnetic, that says para for short. If you continue to cool down, you get an FCC structured ferromagnet. And if you continue to cool down farther, you get a non-magnetic hexagonal close packed phase. So yeah, 1 phase, 2 phase, 3 phases, 4 phases. Although structurally, there's only 2 distinct solid phases, FCC and HCP. Okay, so that's how to read the study. So let's see, what if we heat up at ambient pressure, right? On this scale here, gigapascals, ambient pressure is basically 0, right? Right, this 100 gigapascals is 10 to the 8 pascals, 10 to the 8, and atmospheric pressure is 10 to the 5. So atmospheric pressure is basically along the y-axis here. And as we heat up, we go through a couple transformations. We go from HCP to FCC. We go from FCC ferro to FCC para. And we go from para FCC to liquid. And these are the transformation temperatures, right? Epsilon to gamma. Then there's a magnetic transition at the Curie temperature, and then a melting point, T sub n. So we're just reading phase diagrams. Where do we find data for the heat capacity of cobalt? Lots of places. You've explored some of the databases already here. In this class, let's go with the NIST chemistry web book. It's a very convenient resource. I hope you've used it already. Heat capacity of cobalt. So this is what happens if you go to the NIST website and you follow the links to this solid phase heat capacity of cobalt. And what do you see here? You see a parametric form. There's a polynomial expression. There are the values of the coefficients of the polynomial. And there are 3 different ranges. There's a room temperature to 700K, 700K to 1394, and 1394 to 1768. Based on what we just saw with the phase diagram, would somebody volunteer why are there 3 different ranges given for the heat capacity of cobalt?
Is it because of the different phases?
Because of the different phases. The different phases have different heat capacities. In general, different phases have different heat capacities. Right. So you see this is the non-magnetic HCP. And then there's a little jump in the heat capacity. And we can see that there's a little bit of a jump there in the heat capacity. It jumps to a slightly lower value. And you enter the FCC magnetic phase. And then there's this funny spike. This is a Curie temperature. And above the Curie temperature, there's a real discontinuity in the heat capacity. It comes down. Another thing I'll note here is this data is all well above the DeLong and Petit, right? It starts at 25 and then it goes up. It goes up as high as 55. We're going to talk about that in a minute. So how do you get this data? Where do you think this data came from? Sorry, Catherine?
Experiments.
Yeah, it came from experiments. That's right. It's empirical. This expression like this, A plus B times T plus C times T squared plus D times T cubed plus E over T squared, that's not a first principles solution. That's not a theoretical model. That's just curve fitting, right? That's just curve fitting. So whenever you are dealing with data that has been curve fit, you have to always ask yourself, what is the range of validity? So there's a model that gives you the heat capacity of this magnetic phase. And that model is only valid over the range over which the data has been fit. That's why this database and every other database will always specify the range. These coefficients are good from 700 to minus 1394 Kelvin, right? But if you exceed that range, use that model at your own peril. That's a really important point. Now let's talk a little bit about why this heat capacity is higher than 25. Why is it higher than those other solids? What is it about cobalt? I'll give you a hint. It's not particular to cobalt. There are other metals, there are other materials that have this feature. Anybody know what it is? Anybody?
Is it because it's HCP structured?
No, it's not, although I do like the idea, the suggestion that it's structure dependent. Is there anything else about the system? We've talked about it a little bit. I'll give you a hint. So we talked about ways that energy can be partitioned in lattice vibrations. You have this idea about bond lengths, and as we excite the atoms, there's more energy in those bonds. But there's other ways that atoms can interact with each other, and other ways that they can store energy. So for example, you might have a molecular system, and the molecules can rotate. That doesn't apply to cobalt. You might have an electronic conductor, and the states of the conduction electrons contribute. That's really something that physicists care a lot about. But there's another one here that's particular to cobalt. Anybody?
Magnetism.
Magnetism. Yeah, thanks. So this is what we're gonna. There are others. So anything microscopic on the atomic and molecular level that can store energy, that can be energized, that can be excited, it all factors into the heat capacity. It's all in there. Heat capacity is like this amazing thing that contains so much science. So let's consider a ferromagnet. Such as cobalt. There are other ferromagnets, of course. I don't know why I picked cobalt. All right, now we're going to draw pictures the way we did before with the case of lattice vibrations, except now we're going to consider the magnetic system. So let's consider two scenarios. Scenario one, the magnetic moments. That's what I'm drawing here, magnetic moments. And those can be spin and orbital, are aligned and quiescent. Right? This is a lower energy, lower entropy state. Now what happens if I heat the state up? Let's say this is very low temperature. What happens if I heat it up? Let's pour some energy in. Right. This is the low energy state, sort of like that R naught equilibrium bond lengths was the low energy state. What happens when I heat up? I know this isn't a course on magnetism, so just feel free to guess.
They can change the orientation.
Yeah. Let's say they start. I don't know if that's visible at all. The idea here is that magnetic moments are fluctuating. They're fluctuating, just like the bond lengths were fluctuating before. Now the orientation of the magnetic moments are fluctuating. Right? This is higher energy. Higher entropy. And just like there was a term phonons for the excitations of a crystal lattice structure, we have a term magnons for excitations of magnetic structure. Now, this is that was the beginning, middle, and end of our discussion of magnetism in O2O. We're not going to discuss magnetism, but I did want to make sure you're aware that the heat capacity includes all the interesting things that a material can do, not just vibrate bond lengths, but any other ways that energy can be partitioned into the crystal or amorphous material or liquid or gas or anything. It's all in there. It's all in the heat capacity. So we go back and we look here at the heat capacity of cobalt again, right? We've got this spike. We got this spike at the Curie temperature. And that is associated with all of the fluctuations that you find when a system is just about to order. I think it's really interesting stuff. This excess heat capacity, well above and beyond the Delon and Petit value of like 25, can be largely associated with the magnetic interactions. Okay, that's neat. I think we are done with cobalt and magnetism. Questions before I move on? All right, let's talk about phase transformations. And this is really about using data, but it also leads us into the topic we start on Friday. All right, let's consider something simple and important. Good place to start. Consider solid to liquid transformation in silicon. That's an important material, right? So I looked it up and I found the enthalpy change. Delta H, solid to liquid, at the melting temperature. Somebody, is that positive or negative? Is that an endothermic or an exothermic process, melting?
Endothermic.
Endothermic. You have to put a heat in to melt something, right? Plus at 50.2 kilojoules per mole. I looked it up. This is the change in enthalpy at the equilibrium melting temp. T melting equals 1685 Kelvin. I always remember the Celsius a little bit better. 1412 degrees C. All right, so that's hot, but I'm not too hot. All right, let me ask a question. What is enthalpy change delta H, solid to liquid, for T less than T melting? Right, solidification is exothermic, melting is endothermic. So the question is, how much heat does the solidification process give off when you're solidifying below the melting point? This is highly relevant to a lot of important industrial processes, because often we don't form materials, including silicon, right at the melting point. Often we solidify at a slightly lower temperature. And you have to know this number in order to engineer your process. There's a lot of really good MIT IP on this and a couple spin-off companies that you may be familiar with. So let me just write some stuff down. For the solid phase, the enthalpy of the solid at temperature equals enthalpy of the solid at temperature of melting. This is just what we did about 25 minutes ago, plus the integral from T melting to T, D dummy variable, heat capacity of the solid phase. And for the liquid phase, we have the same type of calculation. Enthalpy of the liquid at a function at temperature equals enthalpy of the liquid at the melting temperature plus, sorry, there I got a little squished, dt prime Cp of the liquid. So again, all the information we need is contained here in these heat capacity data. So the thing we asked to calculate is delta H, solid to liquid, at some temperature. And I'm going to simply combine these results. It is equal to delta H, solid to liquid, at the melting temperature, plus the integral of the heat capacity difference. Heat capacity difference. Heat capacity differences are really important when considering phase transformations. All right, let's look at some silicon data. Let's look at some data for silicon. I downloaded it and plotted it. All right, well, first of all, where would you get thermodynamic data for silicon? Many, many places. Here are two. Here's some data right in the book, in the appendix. Silicon, appendix C or something. What is this data? Silicon, dia to L. Dia to L. What does dia mean in this case? Anybody? I called it solid. I called it S for solid. Why is it here dia?
Does that stand for a diamond-like configuration?
Right. Silicon is a diamond cubic structure. So that's a solid phase of silicon. All right. So a lot of times you need to sort of interpret dia to L, and they use lowercase l, which is always problematic. So I use uppercase L. But anyway, that happens at 1685 Kelvin. There is an entropy of transformation of 29.8, and the units are in the bottom of the table. In this case, it's joules per Kelvin per mole. And there's an enthalpy of transformation of 50.2 kilojoules per mole. I already told you that. You can also look up the values here for the boiling of liquid silicon at atmospheric pressure. There's lots of silicon data here, right, at NIST, and also Springer Materials and Wikipedia. Silicon's really important, so you're going to find the data all over the place. All right, so pardon me. Let me see what comes next. All right, so this is what I'm going to do. I need this heat capacity data, right? I need the heat capacity data, Cp as a function of temperature. So I go over here to the NIST data, and I grab the numbers and I plotted them. So here we go. This is my plot. This I made this in MATLAB. So this is my plot of the heat capacity. What they said it was of liquid silicon as a function of temperature, and here it's the heat capacity of solid silicon as a function of temperature. Now, let me ask you kind of a straw man question. What sort of functional form would capture this trend? What sort of functional form captures this pretty well?
Linear.
Linear, right? All right. What about this? What sort of functional form do I need to capture this data?
Quadratic.
Right, it looks quadratic. Here's a word to the wise. In thermodynamics, as in any science and engineering, you got to always pay attention to the numbers. You always have to pay attention to the numbers, and plots can lie. Let's plot these together. What happened? Same data. You see what happened? The y-axis range here was really teensy tiny. Basically, what this data is telling you is that for all intents and purposes, the heat capacity of liquid silicon is a constant. And the heat capacity of solid silicon is a straight line with a slope. So I'm trying to sneak things in here, lessons that aren't strictly about thermodynamics, lessons in paying attention to significant figures and how data is plotted and how data is modeled and fit and such. So sneaking it in. I marked here what the melting point is. So now we have data. We have heat capacity of the solid, the heat capacity of the liquid, we have the melting point. Let me point something else out. I always told you this stuff comes from measurements, right? This is data, it comes from measurements. That means that the data for liquid may not be reliable for T very far below T melting, right? It might not be possible to supercool silicon so far below the melting point, 1600 degrees or 600 degrees below the melting point in order to take data. So that liquid phase data may not be reliable for far below T melting. And likewise, the solid phase data may not be reliable for T far above T melting. And this comes back again to the range of validity of your models. So when you're professional scientists and engineers, you have to think critically about your data resources. How good are they? Where do they apply and where do they not? All right, so let me switch back to the board and just do some calculations and then we'll get to the answer. All right, so we're going to calculate delta H and we're going to use the thermodynamic data. All right, use thermal data. All right, from NIST. NIST gives it to us in this form like this. CP equals A plus BT plus CT squared plus DT cubed plus E over T squared. This is the general form that NIST gives the data, and many other resources too, not just NIST. And if you're not sick of me saying it yet, you will be soon. This is empirical, right? This is not some sort of quantum first principles result. And NIST normalizes temperature like this. Got to always be careful. Different databases treat temperature different ways. Here it's normalized by 1000 Kelvin. So this lowercase t is unitless. All right. So let's grab the data for these materials we care about. A, joules per Kelvin per mole. B, in joules per Kelvin per mole. C, and so on. Solid, liquid. I'm just grabbing the data from NIST here, just copying over it. So for solid, we get 22.82. For liquid, we got 27.20 for the A parameter. Now the B parameter. For solid, it was 3.90. You'll remember the data was pretty well modeled by a straight line with a finite slope. The liquid, forget it. It looked constant to me. I mean, it's really constant. So likewise, curvature, forget it. Forget it. We're going to approximate that there's no curvature in the data. And so forth and so on for those other parameters. So we're reducing our model to a model with 3 coefficients, right? A line with a slope for the solid and just a fixed value for the liquid. And we are by inspection of the data, ignoring these terms. These terms. Right, this is the sort of thing that I and all my colleagues in academia and industry do every day 10 times a day is you look at data, you got to make a decision. You have to boil down your model. You need something you can solve, and you need to be able to solve it in the time given, right? And sometimes you just have to make decisions. So here's an example. Just make a decision. The data looked like this was a line with a slope and this was a fixed value. All right, you're really sick of me talking about this, so let's just move on to the answer. Delta Cp for solid to liquid as a function of temperature is A liquid minus A solid plus B liquid minus B solid times T plus terms we're ignoring. We're setting the liquid linear coefficient to 0. So this is simply equal to A liquid minus A solid minus B solid. And here I'll make this explicit here. This is T over 1000 K. And finally, delta H solid to liquid T equals delta H solid to liquid at the melting point. And polynomials are easy to integrate. That's one of the reasons why they're used in this case. The heat capacities are expressed as polynomials because they're easy to integrate. That's it. So we've boiled down an important engineering problem to evaluating a polynomial with coefficients that we can look up in the databases. And this is a really important quantity for controlling silicon solidification, which is critical for making computer chips and solar cells. So let me plot the answer. There's the answer plotted, right? I plotted the answer. This is the enthalpy of melting of silicon. There's T melting marked. This is in kilojoules per mole. And I'll tell you, it probably doesn't actually cross over 0. So you look at this data, it's probably only reliable close to the melting point. Okay, so that was just a bit of a walk through some things which you know, you've seen formally, but it's nice to see fleshed out a little bit. And highlighting some important things in this class, using data, plotting data, making approximations, so forth and so on. On Friday, after the exam, we're going to pick up with the introduction to unary phase diagrams and doing a lot of calculating transformation quantities for phase transformation. So this is a lead into that. I'll mention there's one of these mini lectures that is posted on the website called the 3 Ds of thermodynamics. And that's going to start becoming relevant and hopefully helpful because there's going to be a lot of Ds. There's going to be regular D, lowercase Greek d, uppercase Greek d, and they all mean different things. So if you start to find yourself confused over what all these deltas and Ds and have to mean, hopefully that's a good resource for you.